Every galaxy you see is held together by a ghost, this invisible cosmic architect, known as dark matter, dictates the form and fate of every star city in the sky. By the end of this journey, you will understand the hidden blueprint that built our universe. We will uncover how stars defy gravity and why light bends around empty space. This exploration reveals why dark matter is the fundamental sculptor of reality, not just a scientific mystery. What invisible force most captures your imagination? This ghostly hand guides entire galaxies through the cosmic void like a ship steered through dense fog by an unseen pilot. We call this mysterious force dark matter, a substance that does not emit, absorb, or reflect any light at all. It is utterly invisible to every telescope we have ever built, detectable only by the gravitational pull it exerts on the things we can see. The pioneering astronomer Vera Rubin captured the profound nature of this discovery when she reflected, "We have peered into a new world and have seen that it is more mysterious and more complex than we had imagined." So what is it made of? Scientists theorize it could be composed of exotic particles that barely interact with normal matter. Leading candidates have playful names like WIMP, which stands for Weakly Interacting Massive Particles, or Axions, which are hypothetical particles incredibly lighter than an electron. Whatever its true form, it is not a minor component. Dark matter outweighs all the stars, planets, and interstellar dust in the universe by a factor of about 6 to 1. Everything you have ever seen or touched constitutes less than 20% of what is actually out there. The first clue to this staggering reality came from watching how galaxies move. In the 1930s, a sharp-witted astronomer named Fritz Zwicky was studying a giant swarm of galaxies known as the Coma Cluster. He noticed these island universes were whizzing around at speeds that defied all logic. The collective gravity from all the visible stars and gas in the cluster was far too weak to hold them together. According to the known laws of physics, the cluster should have flown apart, its galaxies scattered into the emptiness. Yet it remained firmly bound. Zwicky concluded that some unseen mass, which he named Dunkel Materie, or dark matter, must be providing the extra gravitational glue. This was the moment cosmology was forever changed. What if everything we see, every brilliant spiral and glowing cloud, is just the visible decoration on a much larger, hidden structure? To understand how this invisible architecture truly shapes every galaxy, we must first look back at the historical roots of this monumental discovery. Fritz Zwicky's proposal of Dunkel Materie was met with deep skepticism. The idea of an invisible, dominant form of matter seemed too fantastical for many in the scientific community, and for decades it remained a fringe hypothesis. The evidence, however, refused to fade away. It was the meticulous work of astronomer Vera Rubin and her colleague Kent Ford that finally brought dark matter into the glaring light of mainstream science. They were not looking at a distant cluster, but at individual galaxies, specifically their rotation. They expected to see stars closer to a galaxy's center orbiting at tremendous speeds, while stars farther out in the sparse outskirts would move more slowly, just as Pluto takes its time on a long, lazy orbit around our Sun compared to the inner planets. What they found was astonishing. Whether a star was near the bright core or far out in the dim galactic halo, its orbital speed was almost exactly the same. This constant velocity defied every prediction of Newtonian gravity based on the galaxy's visible mass. It was as if every car on a vast circular racetrack, regardless of whether it was on the inner lane or the outer lane, was magically maintaining the exact same speed. The only explanation was that each galaxy was embedded within a massive, invisible sphere of dark matter, a halo whose gravity was orchestrating the motion of the stars from the shadows. This was the clincher, the undeniable proof that something profound was missing from our inventory of the cosmos. Yet, the final, most dramatic confirmation came from a violent event far out in space. Astronomers observed two giant clusters of galaxies, each containing trillions of stars, colliding in a system known as the Bullet Cluster. In this cosmic wreck, the normal matter, the hot gas that glows in X-rays, slammed into itself and got stuck in the middle. But the dark matter, which does not interact with itself or anything else except through gravity, sailed right through the collision. By mapping the gravitational lensing, the way the cluster's mass bent light from galaxies behind it, astronomers could trace where the mass actually was. They found the bulk of the mass, the dark matter, was in two separate clouds far away from the visible gas. It was a direct image of the dark component, separated from the ordinary stuff and shown to be real. These pioneering observations, from Zwicky's clusters to Rubin's rotations and the Bullet Cluster's snapshot, completely transformed our cosmic blueprint. We went from a universe of visible stars and gas to one dominated by an invisible architecture. This discovery leads us to the next great question. If dark matter is everywhere, how is it arranged? The answer lies in a structure so vast it connects every galaxy in the cosmos. The universe began not with a grand design, but with a whisper. In the fiery aftermath of the Big Bang, the cosmos was a nearly smooth sea of energy and particles. Yet, woven into that primordial soup were the faintest ripples, tiny variations in density. These were the seeds of everything to come, but they were far too weak to build a galaxy on their own. They needed an architect, a force that could amplify their subtle signal into a cosmic shout. That force was dark matter. Its relentless gravity acted on those tiny flaws, pulling more and more of the invisible substance into those slightly denser regions. Over billions of years, what began as a faint cosmic fingerprint grew into the backbone of the universe. As the renowned cosmologist Carlos Frenk explains, dark matter provides the scaffolding upon which galaxies are built. This is not a minor role, it is the fundamental framework. Think of a city under construction. You first erect the steel skeleton, the invisible support that defines the entire shape and scale of the future skyline. Only after that framework is secure do you add the walls, the windows, the brilliant lights. In our universe, dark matter is that steel skeleton. The stars and glowing gas we see are merely the decorative facade built upon it. This process starts with dark matter halos, vast spherical clouds of this mysterious substance. Each halo acts as a gravitational pit, a deep well that tirelessly pulls in the normal, or baryonic, matter, the hydrogen gas and dust that will eventually ignite into stars. Without this invisible anchor, the primordial gas would simply have drifted apart, scattered by the universe's expansion, never coalescing into the brilliant structures we see today. Our most powerful supercomputers have simulated this epic construction project. Landmark simulations like the Millennium Run take the known laws of physics and the initial conditions of the universe, and then they let time fly forward. The result is always the same. The dark matter forms an immense cosmic web, a labyrinth of dense filaments connecting at glittering nodes where galaxies cluster, all separated by vast, empty voids. The stunning agreement between these virtual universes and the one we observe is one of the strongest pieces of evidence that we are on the right track. This structure forms in a specific way thanks to what scientists call cold dark matter. The term cold means these particles were moving sluggishly in the early universe. This was crucial. Their slow speed allowed them to readily clump together, starting with small, asteroid-sized halos. Through an endless cycle of mergers and acquisitions, these small halos hierarchically assembled into the majestic galaxies we see today. It was a bottom-up construction, with dark matter laying the foundation for every structure, from the smallest dwarf galaxy to the largest cluster. So, what if this unseen architect had never shown up for work? How would our night sky look if dark matter did not exist? The answer is profoundly dark and empty. There would be no grand spiral galaxies, no brilliant clusters, and likely no stars at all. The faint ripples from the Big Bang would have remained just that, far too weak to gather the gas needed to spark a single sun. Our Milky Way would never have formed, and the universe would be a lonely, diffuse sea of fading hydrogen, with no one to witness its expanse. This invisible framework does not just build galaxies, however. It also dictates how they move, a truth written in the very speed of their stars. The stars themselves were the first to reveal the ghost. As astronomers began meticulously mapping the orbital speeds of stars within spiral galaxies like our own, they encountered a puzzle that defied the established laws of motion. They expected to see a clear pattern, much like our solar system. Close to the Sun, planets like Mercury and Venus whip around at blistering speeds, while distant, cold worlds like Neptune and Pluto crawl along their vast, slow orbits. This is Kepler's law in action, a direct result of gravity weakening with distance. If a galaxy were made only of the stars and gas we can see, the same rule should apply. Stars near the bright center should race, while those in the sparse outer reaches should drift lazily. The data told a completely different story. When they measured the velocities using the Doppler shift of starlight, a technique that reveals whether a star is moving toward us or away from us by the subtle stretching or compressing of its light, they found rotation curves that were almost perfectly flat. A star tens of thousands of light years from the galactic core was orbiting just as fast as a star near the center. It was as if the entire galaxy, from its brilliant heart to its dim outskirts, was a single, solid plate spinning all at once. This was impossible under the known physics of gravity. The visible mass was completely insufficient to hold these far-flung stars in such swift, tight orbits. The only logical conclusion was that there was extra mass, a tremendous amount of it, that we could not see. Vera Rubin, whose work was central to this discovery, put it perfectly when she said, "What you see in a spiral galaxy is not what you get." Our nearest large galactic neighbor, the Andromeda galaxy, provides a stunning example. When we chart the speeds of its stars, we find they all orbit as if they are trapped within a colossal, invisible sphere of mass, a dark matter halo that extends far beyond the galaxy's visible edge. The mathematics is inescapable. To account for the observed rotation, dark matter must make up roughly 85% of the total mass in a typical galaxy. The glittering stars and glowing gas we admire are just the visible tracer, the glitter on the surface of a deep, dark ocean. So the next time you look up at the band of the Milky Way, consider this. The very reason those distant stars can race around the galactic center without flying off into the void is the gravitational embrace of an invisible giant. This hidden mass does not just shape majestic spirals, it dictates the very existence of every type of galaxy in the sky, from the smallest, faintest dwarfs to the largest, most chaotic ellipticals. A sculptor's unseen hand determines the final form of the clay, and so it is with dark matter and galaxies. Its invisible architecture dictates whether a galaxy will become a majestic spiral, a smooth elliptical, or a chaotic irregular. Astronomer Sandra Faber captured this perfectly, stating that dark matter sets the stage for galaxy evolution. It is the cosmic stage director that determines the shape of the entire play. Consider our own Milky Way, a classic spiral galaxy. Its beautiful, thin disk of stars and gas spins at incredible speeds, a motion that should tear it apart. The only thing holding this delicate structure together is the immense gravitational grip of its spherical dark matter halo. This invisible sphere acts like an unseen mold, keeping the fast-moving stars on their circular tracks and maintaining the galaxy's iconic pinwheel shape. Without this dark matter scaffold, our galaxy would have flown into pieces eons ago. Now look at the Sombrero Galaxy, a brilliant example of an elliptical shape. Here, the stars do not orbit in an orderly disk but swarm in a vast, three-dimensional cloud, buzzing around the center in every direction. The dark matter halo in such galaxies is equally massive, but its influence is felt differently. Often found in the crowded environments of galaxy clusters, these ellipticals are shaped by relentless mergers and interactions, processes where dark matter provides the deep gravitational well that binds the chaotic stellar swarm together, leading to their rounded, featureless appearance. Then there are the irregular galaxies, the cosmic misfits with no defined shape. These are often the sites of recent gravitational violence, where dark matter has orchestrated near misses or full collisions. Its gravity creates immense tidal forces, pulling and stretching the visible gas and stars into bizarre, twisted forms. This variation in shape is deeply tied to the ratio of dark matter to normal matter. A spiral galaxy like the Milky Way has a balanced, though dark matter-dominated, makeup, allowing for a stable disk. Some small, faint dwarf galaxies, however, are almost entirely made of dark matter, with just a few visible stars, making them incredibly diffuse and hard to find. Others, formed in especially dense regions of the early universe, manage to gather so much normal gas that their stars outweigh their dark matter content in the inner regions, leading to a completely different structure and history. So why do some galaxies have more dark matter than others? The answer lies in the chaotic conditions of their birth within the cosmic web. This variation in the invisible component is the key to understanding the stunning diversity we see in the night sky. But this hidden sculptor does more than just define shapes. It also forges the very hearts of galaxies, creating environments so extreme they trap light itself. That immense, invisible sphere of dark matter surrounding our galaxy is far more than just a simple cloud. It is a dynamic, deeply structured entity known as a dark matter halo, a cosmic cocoon that cradles every galaxy. Think of it not as a uniform fog, but as a complex, layered structure with its own hidden geography. Our most advanced computer simulations, like the landmark Aquarius project, have allowed us to peer into the anatomy of these halos. They reveal a stunning reality. A dark matter halo is not smooth and featureless. Instead, it contains a rich tapestry of substructure, a vast collection of smaller, denser clumps of dark matter that orbit within the larger halo like invisible moons. These are the leftover building blocks from the galaxy's own violent assembly, the fossils of its formation still held in its gravitational embrace. The density of this dark matter is not the same everywhere. It follows a predictable pattern, a universal rule known as the Navarro-Frenk-White Profile. This principle tells us that the dark matter is most densely packed at the very center of the halo, and its concentration steadily decreases as you move outward into the galactic suburbs and beyond. It is a gradient of gravity, strongest at the core and fading into the void. The sheer scale and mass of this halo is what ultimately dictates a galaxy's destiny. Our own Milky Way provides the perfect example. The halo enveloping our home is estimated to be about 10 times more massive than all its visible stars, gas, and dust combined. This incredible weight creates a profound gravitational well, a pit so deep it dictates the motions of everything bound to our galaxy. The orbits of distant globular clusters, those ancient swarms of stars, and the paths of small, satellite dwarf galaxies are all choreographed by the pull of this unseen halo. They are not orbiting the bright disk of the Milky Way you see in the night sky. They are tracing the contours of its immense, dark foundation. This halo acts as a cosmic anchor, its relentless gravity preventing the galaxy's rapidly spinning disk from flinging its stars into the intergalactic void. Without this invisible cocoon, the majestic spiral we call home would simply unravel, its stars scattering like embers from a spinning wheel. But if we cannot see this halo, how can we possibly map its intricate structure and confirm its existence? The answer lies in one of the most elegant phenomena in the universe, a natural telescope forged by gravity itself. Gravity itself becomes the lens through which we finally see the unseen. The immense mass of a dark matter halo warps the very fabric of space-time around it, creating a natural, cosmic magnifying glass. This phenomenon, predicted by Einstein's theory of general relativity, is called gravitational lensing. As the renowned astrophysicist Kip Thorne put it, gravitational lensing is nature's way of showing us the unseen. When light from a distant galaxy travels toward us, its path is not perfectly straight. It bends and curves as it passes through the gravitational field of a massive foreground object, like a dark matter halo. This distortion creates telltale signs in the images captured by our most powerful telescopes. In its most dramatic form, known as strong lensing, the effect is breathtaking. Enormous galaxy clusters, such as Abell 1689, act as cosmic lenses so powerful they can twist the light from background galaxies into brilliant arcs, multiple images, and even perfect rings of light called Einstein rings. It is as if you are looking at a distant street lamp through the bottom of a wine glass, and its single light is smeared into a shimmering circle. These arcs are not the galaxies themselves, but mirages, ghostly projections sculpted by the invisible mass of the cluster. But strong lensing is a rare and spectacular event. More common and just as revealing is weak lensing. Here, the dark matter halo of a single galaxy or a small group is not massive enough to create dramatic arcs. Instead, its gravity imposes a subtle, coherent distortion on the shapes of thousands of faint background galaxies. Individually, each galaxy's slight stretch is almost invisible, lost in their natural, random orientations. But by analyzing the patterns across a vast sea of galaxies, astronomers can detect the collective shearing effect, a statistical whisper that reveals the shape and distribution of the intervening dark matter. This is the primary technique used in monumental projects like the Dark Energy Survey. By meticulously measuring the shapes of hundreds of millions of galaxies, these surveys allow scientists to create detailed maps of dark matter's invisible architecture across huge swaths of the sky. The most iconic proof of this method came from the Bullet Cluster. In that violent collision, astronomers used weak gravitational lensing to trace where the mass was located. The map showed two distinct clouds of mass that had sailed right through the wreckage of the colliding gas, perfectly aligning with the positions of the two clusters' galaxies. This was the smoking gun. The lensing revealed that the true mass, the dark matter, was completely detached from the visible stuff, proving its existence beyond any reasonable doubt. So how does this bending of light actually allow us to see the invisible? It translates gravity into a visible signal. By measuring how much the light is bent, we can literally weigh the dark matter halo, calculating its mass and mapping its contours without ever detecting a single particle of it. This cosmic cartography of the unseen brings us to the ultimate question. What is this mysterious substance actually made of? These cosmic detectives use a powerful toolkit to measure the ghost. Each method provides a different clue, constraining the properties of dark matter from multiple angles. The first and most direct line of evidence comes from watching things move. Galaxy rotation curves, the very observations that Vera Rubin pioneered, remain a foundational tool. By measuring the orbital speeds of stars and gas clouds within a galaxy, astronomers perform a simple but profound calculation. They can weigh the galaxy. The faster the stars orbit, the more mass must be present to hold them in place. The shocking result, as we have seen, is that the calculated mass is always far greater than the total mass of all the visible components. This technique gives us a precise measurement of dark matter's influence on a local galactic scale. For the large-scale structure of the universe, gravitational lensing is the premier instrument. It allows us to map the invisible cosmic web directly. By observing how the light from distant galaxies is bent and distorted by foreground mass, we can create a three-dimensional chart of the dark matter distribution across billions of light-years. This is like taking an X-ray of the cosmos, revealing the skeletal structure upon which galaxies are built. The Hubble Space Telescope has been instrumental in this effort, its sharp vision providing countless examples of both strong and weak lensing that have cemented our understanding of dark matter's architecture. To peer into the ancient universe, scientists study the cosmic microwave background, the faint afterglow of the Big Bang. The Planck space mission provided a detailed baby picture of the cosmos when it was only 380,000 years old. The subtle patterns in this radiation, tiny fluctuations in temperature, are a frozen record of the density ripples that would later grow into galaxies. As a Planck collaboration scientist noted, the characteristics of these fluctuations tell us precisely how much dark matter existed in the early universe. The data reveals that ordinary matter makes up only about 5% of the cosmos, while dark matter constitutes about 27%. This early universe accounting matches perfectly with what we see from galaxy motions and lensing today, providing a consistent story across 14 billion years. Then there is the hunt for the particle itself, deep underground, in labs shielded from cosmic rays by a mile of rock. Experiments like LUX-ZEPLIN wait in profound silence. These ultra-sensitive detectors are filled with liquid xenon, hoping to catch the rare, faint ping of a dark matter particle, perhaps a WIMP, colliding with an atomic nucleus. It is a search for a direct, undeniable signal. Meanwhile, in space, telescopes like the Fermi Gamma Ray Space Telescope look for indirect evidence. They scan the skies for unexpected bursts of gamma rays that could be produced if two dark matter particles were to annihilate each other upon collision, a process that would convert their mass into pure energy. And at particle colliders like the Large Hadron Collider, physicists try to create dark matter particles by smashing ordinary particles together at nearly the speed of light, hoping the immense energy will conjure this elusive substance into detectable existence. Each technique probes a different facet. Rotation curves tell us dark matter is there. Gravitational lensing shows us where it is. The cosmic microwave background tells us how much there is. And the direct detection experiments are trying to figure out what it is. This multi-pronged investigation, this convergence of evidence from the motions of stars, the bending of light, and the echo of the Big Bang, leaves no doubt about the reality of this invisible component. The next great frontier lies in understanding how this hidden mass orchestrates the most massive structures in the universe, the colossal cities of galaxies known as clusters. These colossal cities of galaxies are held together by an unseen kind of gravity. A single galaxy cluster is a breathtaking metropolis, home to hundreds or even thousands of individual galaxies, all swarming within a common volume of space. Yet the brilliant galaxies themselves are merely the glittering lights of this cosmic city. they are outnumbered and outweighed by a far more massive, invisible resident. As the astronomer Margaret Geller observed, dark matter is the skeleton upon which clusters are built. It is the hidden infrastructure, the gravitational glue that binds these vast communities together. Without it, the entire structure would fly apart in a cosmic instant. The evidence for this is written in the frantic motion of the galaxies themselves. Each galaxy within a cluster is moving at a tremendous speed, often thousands of kilometers per second. If you were to add up the gravity from all the visible stars in all those galaxies, it would be utterly insufficient to hold them at such velocities. The collective pull is far too weak. The galaxies should have scattered into the void long ago, like a crowd dispersing when a room loses its walls. The fact that they remain, that these clusters are stable over billions of years, proves they are embedded within a massive, invisible sphere of dark matter whose gravity is strong enough to keep everyone in check. There is another, even more pervasive clue within the cluster, a seething ocean of superheated gas known as the intra-cluster medium. This gas is so incredibly hot, reaching temperatures of tens of millions of degrees, that it glows not in visible light but in powerful X-rays. When we point our X-ray telescopes at a cluster like the nearby Virgo cluster, we see a vast, diffuse cloud of this brilliant gas enveloping all the galaxies. For this gas to remain so hot and confined within the cluster, rather than simply boiling away into space, it must be trapped by an immense gravitational well. When astronomers calculate the mass needed to create that deep well of gravity, they find once again that the visible galaxies account for only a tiny fraction. Dark matter provides the dominant gravitational potential, the deep pit that holds both the galaxies and the searing gas in its grasp. In the Virgo cluster, measurements consistently show that dark matter makes up over 80% of the total mass. The most dramatic demonstrations of this invisible architecture come from watching these cosmic cities collide. We see this in systems like the Bullet cluster, where two galaxy clusters have slammed into one another. In these incredible events, the different components behave in starkly different ways. The clouds of hot intra-cluster gas, the normal matter, crash into each other. They experience friction, slow down, and get stuck in the middle of the collision, glowing brightly in our X-ray observations. But the dark matter and the galaxies, which are mostly empty space, do not interact this way. They simply pass right through the chaos. Using gravitational lensing, we can map where the true mass ends up after the collision. The maps reveal that the bulk of the mass, the dark matter, is not in the center with the gas. It has sailed ahead, remaining perfectly aligned with the galaxies themselves. This provides a clean, visual separation of the dark and the ordinary matter, a perfect snapshot that confirms dark matter is a real, physical substance that governs the dynamics of the largest structures we know. So what happens when these titanic communities of galaxies, each with its own dark matter skeleton, crash together? The answer reshapes our understanding of how galaxies themselves are forged and transformed. Long before the first star flickered to life, the universe was a silent, featureless expanse of hydrogen and helium gas, cooling in the aftermath of creation. The stage was set, but the actors were missing. The transformation from this cosmic blank slate to a sky filled with galaxies began with the faintest of whispers in the dark. The slight overdensities in the dark matter, those tiny ripples from the Big Bang, were the universe's only blueprint. Their gravity, patient and relentless, began to pull. They gathered more dark matter to themselves, growing slowly into invisible clumps, and in doing so, they carved out deep gravitational wells in the fabric of space. It was into these wells that the ordinary matter, the baryonic gas, began to flow. As the cosmologist Simon White profoundly stated, dark matter halos are the cradles of galaxy formation. They were the nurseries where everything we see was born. This entire process is the heart of our leading cosmic model, Lambda-CDM, where cold dark matter provides the foundational structure. The cold nature of the particles was vital because they moved sluggishly. They could readily clump together without the disruptive pressure that affects normal matter. This allowed the dark matter to form the first structures, the gravitational anchors, long before the gas could collapse on its own. After the cosmic microwave background was released, the universe entered its dark ages, a period devoid of starlight. But in the silence, the dark matter scaffolding was steadily rising. Within these growing halos, the infalling gas was compressed and heated. When a halo reached a critical mass, its gravitational pull was finally strong enough to trigger the collapse of dense gas clouds, sparking nuclear fusion and igniting the very first stars. These brilliant, massive stars were the beacons of the cosmic dawn, ending the dark ages and flooding the universe with its first light. Our most sophisticated supercomputer simulations, like Illustris TNG, show this hierarchical buildup in stunning detail. They reveal a universe where tiny dark matter halos form first. Through an endless, graceful dance of mergers and acquisitions, these small halos coalesce into larger and larger structures. A small clump would merge with a neighbor, its dark matter and gas combining. This merger would stir up the gas reservoir, triggering intense waves of new star formation and building up the galactic core. It was a bottom-up construction project, with dark matter as the foreman, orchestrating the assembly of galaxies from the smallest fragments into the majestic spirals and ellipticals we recognize today. The recent observations from the James Webb Space Telescope provide a breathtaking glimpse into this ancient era. It is seeing galaxies at incredibly high redshifts, meaning we are observing them as they were just a few 100 million years after the Big Bang. The fact that such large, bright galaxies existed so early is a powerful test for our models of dark matter. Their very existence, their rapid formation, points to the efficiency of those initial dark matter seeds in gathering gas and igniting stars with surprising speed. Every galaxy we see, from the most distant smudge of light in a JWST image to our own Milky Way, owes its existence to this unseen architect. Dark matter did not just influence galaxy formation. It dictated it, setting the stage for the entire cosmic evolution that followed. Its gravitational blueprint determined where galaxies would form, how quickly they would grow, and ultimately, how they would be distributed across the vast expanse of the cosmos in an immense, interconnected web. This vast cosmic web is the ultimate expression of dark matter's architectural power. The universe is not a random scattering of galaxies, but a magnificent, interconnected structure, a spiderweb of staggering scale. Glowing galaxies are strung like dewdrops along invisible filaments of dark matter, connecting at dense nodes where thousands of galaxies cluster, all surrounding immense, empty voids of near-nothingness. This is the large-scale structure of the cosmos, a pattern shaped over billions of years by the relentless gravity of the invisible. As physicist J. Richard Gott noted, the cosmic web is the fingerprint of dark matter. That fingerprint was first imprinted as minuscule fluctuations in the cosmic microwave background, the faint afterglow of the Big Bang. Those tiny ripples in density were the only blueprint, and dark matter's gravity was the force that amplified them, pulling more and more invisible mass into the slightly denser regions. Over cosmic time, what began as a faint whisper grew into the shouting vastness of the web we observe today. Our confirmation of this grand design comes from monumental galaxy surveys like the Sloan Digital Sky Survey. This project has meticulously mapped the positions of millions of galaxies, and the resulting three-dimensional charts reveal the web with breathtaking clarity. The data shows a sponge-like structure, a labyrinth of dark matter filaments and clusters that matches the predictions of our models with stunning accuracy, confirming dark matter's predictive power. Within this web, each component has a distinct role. The filaments themselves are the cosmic highways, the places where dark matter's gravity guides gas flows and orchestrates the formation of new galaxies. At the intersections of these filaments, where the dark matter is densest, we find the great cities of the universe, the massive galaxy clusters, and between it all stretch the voids, incomprehensibly vast regions largely devoid of both dark and normal matter, the empty deserts of space. A stunning example of this architecture is the Sloan Great Wall, one of the largest known structures in the universe. This colossal filament is a staggering wall of galaxies over 1 billion light-years long. It is not a physical wall, of course, but a gravitationally bound chain within the cosmic web, a single thread in dark matter's grand tapestry. So, how does this intricate web influence the very journey of light across the universe? The answer lies in the specific way dark matter is packed into every thread and node of this structure. The invisible cocoon enveloping a galaxy is not a uniform fog. It has its own internal geography, a specific pattern of density that dictates the strength of its gravitational pull at every point. Picture a planet like Earth, with its atmosphere thick and heavy at the surface, steadily thinning out until it fades into the vacuum of space. A dark matter halo follows a similar, though far more mysterious, gradient. This predictable pattern of distribution is known as a density profile, and it is the key to understanding the halo's hidden architecture. The most successful model for this is called the Navarro-Frenk-White Profile, named for the astrophysicists who discovered its universality in supercomputer simulations. Giulio Navarro, one of its creators, noted that this profile emerges naturally, regardless of the halo's mass or merger history. It is a fundamental signature of how cold dark matter arranges itself under gravity's rule. The NFW profile is defined by a distinct shape, a cusp. This means the density of dark matter rises sharply, increasingly and inexorably, as you approach the very center of the galactic core. It does not plateau. It forms a steep, cuspy peak of invisible mass right at the heart of the galaxy. From that central cusp, the density then falls off steadily as you move outward through the halo, creating a specific gravitational landscape that stars and gas must navigate. Yet nature sometimes presents a different picture. Astronomers studying small, faint dwarf galaxies often find evidence for what are called core profiles. Instead of a steep cusp of dark matter at the center, these galaxies seem to have a flatter, more constant density in their inner regions. This is not a refutation of dark matter, but a clue that other forces are at work. The intense bursts of energy from supernova or the powerful gravitational kicks from merging black holes can potentially stir up the central regions. This astrophysical feedback may act like a cosmic spoon, stirring the dark matter and smoothing out the central cusp into a shallower core over billions of years. We measure these subtle distributions using the same tools that reveal dark matter's existence. The rotation curves of stars and gas clouds trace the gravitational pull within a galaxy, telling us how much mass is enclosed at different distances from the center. Simultaneously, precise weak gravitational lensing studies map the halo's mass distribution on larger scales from the outskirts all the way in. The dwarf galaxy Draco, a small satellite of our Milky Way, provides a compelling case. The stars within Draco are moving with unexpectedly high velocities, a phenomenon known as velocity dispersion. This frantic motion indicates they are being tossed about by a powerful gravitational field. The visible stars in Draco are far too few to create such a deep well of gravity. The only explanation is that Draco is absolutely dominated by a massive, dense core of dark matter, making it one of the most dark matter-rich objects we know. The precise distribution of this invisible mass is not just a detail. It is the bedrock of galactic stability. A steep NFW cusp can anchor a rapidly spinning disk, providing the intense central gravity needed to maintain a galaxy's elegant spiral form. A flatter core profile, on the other hand, might lead to a very different dynamic, potentially making a galaxy more susceptible to disruption from close encounters or internal instabilities. This tension between the predicted cusps and the observed cores in some galaxies is one of the most active puzzles in modern cosmology, a small-scale challenge that pushes our understanding of both dark matter and galaxy evolution to its limits. If dark matter's distribution is so crucial, what happens when these halos themselves are put to the ultimate test, forced to reveal their nature not by their structure, but by their interactions with one another? The universe's grand design holds tiny, stubborn flaws. On the vast scales of galaxy clusters and the cosmic web, our model of cold dark matter is a spectacular success. But when we zoom into the smallest galaxies, the picture blurs with puzzling inconsistencies. Astronomer Stacy McGaw captures this challenge perfectly, noting that the data forces us to rethink dark matter on small scales. Two problems in particular stand out, challenging our understanding of this invisible architect. The first is known as the cusp core problem. Our most sophisticated simulations predict that dark matter halos, especially those around faint dwarf galaxies, should have a steep density profile. According to the Navarro-Frenk-White model, the dark matter should be packed into a sharp, dense cusp at the very center of the galaxy. But when we observe the motions of stars within many of these dwarfs, the story is different. The data often suggests a flatter, more constant density in the core, as if someone has taken a spoon and stirred the very heart of the dark matter halo, smoothing out its central peak. The second puzzle is the missing satellites problem. When we simulate the formation of a galaxy like our Milky Way within a cold, dark matter universe, the results are striking. The simulations predict that our galaxy should be surrounded by a bustling swarm of hundreds of small, dark matter clumps, each one potentially hosting a faint dwarf galaxy. Yet, when we look at our own cosmic neighborhood, we only see a few dozen of these satellite galaxies. For a long time, it seemed as if the vast majority of these predicted dark matter halos were completely dark, utterly devoid of stars, or perhaps missing altogether. How can we resolve these contradictions between our powerful simulations and direct observation? One compelling idea involves the dynamic role of normal matter. This solution is called baryonic feedback. In the early lives of small galaxies, waves of supernova explosions would have been tremendously powerful. These stellar cataclysms can blow enormous winds, pushing the ordinary gas out of the central regions. As this gas is violently ejected, the changing gravitational potential can literally drag the dark matter with it, pulling it outward and effectively erasing the dense central cusp, transforming it into a shallower core. It is a cosmic remodeling job where the actions of the visible stars reshape their invisible foundation. For the missing satellites, the solution might be that most of those small dark matter halos did form, just as the simulations predict, but they simply failed to light up. Perhaps the ultraviolet radiation from the first galaxies heated the primordial gas so efficiently that it could not cool and collapse to form stars within the smallest, weakest halos. This would leave them as truly dark galaxies, invisible to our telescopes. Recent, deeper sky surveys like the Dark Energy Survey have, in fact, begun to find more of these ultra-faint dwarf satellites around the Milky Way, slowly chipping away at the missing satellites problem. But what if the solution is more fundamental? What if dark matter itself is not completely cold and collisionless? Some physicists are exploring models of self-interacting dark matter. In this scenario, dark matter particles could occasionally bounce off one another, a subtle interaction that would smooth out the central cusps of small halos into cores, and could also strip dark matter from the smallest satellites, making them even dimmer and harder to see. Could dark matter have properties we have not yet even imagined? This question pushes scientists to the frontier, where the very nature of the invisible cosmos is up for debate. Perhaps Einstein's gravity is not the final word. A small but determined group of physicists proposes a radical alternative. What if dark matter does not exist at all? What if instead we are witnessing the limits of our understanding of gravity itself? This is the compelling premise of modified Newtonian dynamics, or MND. Its founder, physicist Mordechai Milgrom, argued that we do not need invisible matter if we accept that gravity behaves differently at the extremely low accelerations found in the outer reaches of galaxies. Milgrom stated that his formula was crafted to explain galaxy rotation curves without dark matter, and it does so with striking precision. In many spiral galaxies, MND's simple adjustment to the laws of motion predicts the flat rotation curves perfectly, matching the observed speeds of stars without invoking a single particle of unseen mass. It is an elegant solution that cuts the cosmic budget, declaring the universe to be made only of what we can see. Yet for all its elegance on the galactic scale, MND faces profound challenges when faced with the full breadth of cosmic evidence. It struggles to explain the immense gravitational pull within giant galaxy clusters, where the visible mass is still far too little to hold the searing hot gas without some form of dark matter. It cannot easily account for the detailed pattern of the cosmic microwave background, the baby picture of the universe that requires dark matter to form the seeds of galaxies. And it has difficulty with the clean, visual proof from the bullet cluster, where the gravitational lensing clearly shows the mass separated from the normal matter, a direct signature of something unseen. Other theories have emerged in this bold landscape of alternatives. Emergent gravity suggests that gravity is not a fundamental force, but a side effect of the quantum information stored in the fabric of space-time. Tensor vector scalar theories introduce new fields that modify gravity in complex ways. Each offers a different path to explain the cosmic motions without dark matter. The debate was sharpened by the discovery of a bizarre galaxy known as NGC 1052DF2. This ultra-diffuse galaxy appeared, at first, to have almost no dark matter at all. Its stars were moving so slowly that the visible mass seemed sufficient to account for its gravity. For a moment, it looked like a fatal blow to dark matter, proof that galaxies could exist without this invisible scaffold. But later studies suggested its distance may have been miscalculated, and with a revised distance, the strange galaxy might fit back into the standard model. This back and forth highlights the dynamic, often messy process of science at its frontier. So why does dark matter remain the dominant explanation despite these intriguing challenges? No single alternative can match the sheer breadth of its success. Dark matter provides a single, unifying framework that explains galaxy rotations, the bending of light in lensing events, the large-scale structure of the cosmic web, and the precise fluctuations in the ancient afterglow of the Big Bang. It is the one idea that builds a coherent story from the smallest dwarf galaxy to the largest cluster. This resilience points toward a deeper truth. Dark matter is not just a placeholder for our ignorance. It behaves like a real, physical substance that can be separated from ordinary matter, as the bullet cluster shows, and that must have a specific particle nature. The hunt, therefore, is no longer just about proving it exists, but about discovering what it is made of, deep underground, in a silence broken only by the faint whisper of a particle. The greatest hunt in physics is underway. Scientists are searching for the identity of dark matter, probing a hidden particle zoo where exotic candidates could finally solve this cosmic puzzle. The leading contender for decades has been the WIMP, short for Weakly Interacting Massive Particle, theorized to interact only through the weak nuclear force and gravity. A WIMP would be a heavy particle, perhaps 100 times the mass of a proton. Its appeal lies in a beautiful coincidence physicists call the WIMP miracle. As theorist Lisa Randall explained, the relic density of WIMP left over from the Big Bang naturally matches the amount of dark matter we observe in the universe today. It is as if the cosmos itself left us a perfect clue, but WIMP are not the only players in this game. Another fascinating candidate is the Axion, a hypothetical particle born from a solution to a different puzzle in quantum chromodynamics. Axions are the ghosts of the ghost. They would be incredibly light, potentially a trillionth of an electron's mass, and would behave less like discrete particles and more like a pervasive, wave-like cosmic field. Other ideas populate the theoretical zoo, from sterile neutrinos that barely interact with anything to primordial black holes, tiny remnants from the universe's first moments. How do we catch something that is fundamentally invisible? The search is conducted on 3 fronts. The most direct approach uses ultrasensitive detectors buried deep in mines or under mountains, shielded from cosmic rays. Experiments like LUX-ZEPLIN and Xeno-NNT use giant vats of liquid xenon, waiting for the minuscule flash of light and charge that would signal a rare collision between a dark matter particle and an atomic nucleus. It is like listening for a single, specific note in a universe of noise. The second method is indirect. Telescopes in space and on the ground scan the skies for unusual signals, like an excess of gamma rays or positrons, that could be the signature of dark matter particles annihilating each other in the dense heart of our galaxy or in nearby dwarf galaxies. The third approach is to create it. The Large Hadron Collider smashes protons together at near light speed, hoping that the immense energy will conjure dark matter particles into detectable existence. This multi-pronged effort has produced tantalizing yet controversial hints. For over 2 decades, the Dama/Libra experiment in Italy has reported a persistent, modulating signal that peaks every June and fades every December. The team argues this annual modulation is the telltale sign of Earth moving through a galactic wind of dark matter. Yet no other experiment has been able to confirm this result, leaving the physics community deeply divided on its meaning. With so many possibilities and no definitive detection, we are forced to ask a profound question. What if dark matter is not one single thing? Could our universe's invisible architecture be built from a mixture of components, a cocktail of WIMP, Axions, and other exotics? This very curiosity drives us to look for the ultimate test, one where dark matter is forced to reveal its nature not in the lab, but in the most violent theaters of the cosmos where entire galaxies collide. These cosmic collisions are the ultimate experiments in dark matter physics. When 2 galaxies meet, they engage in a slow, graceful dance that unfolds over hundreds of millions of years. It is a spectacle of creation and destruction, and within this chaos, the invisible architect reveals its fundamental nature. Astronomer Douglas Clow, reflecting on the bullet cluster, stated, "This is the most direct evidence for dark matter." His words capture the power of these events, where we can watch dark matter and normal matter behave in starkly different ways. In a galactic merger, the stars, vast as they are mostly empty space. They slip past one another like 2 swarms of bees. their paths altered by gravity but rarely colliding. The gas, however, is a different story. Immense clouds of interstellar hydrogen slam together, compressing and heating to millions of degrees until they glow with a fierce X-ray light. This is the normal, baryonic matter interacting with itself, creating friction and slowing down. But the dark matter halos making up most of the mass tell a different tale. They are collisionless. Since dark matter does not interact via the electromagnetic force, it feels no friction. The particles simply pass through one another, and the two halos, detected only by their gravitational lensing signatures, sail right through the violent encounter. We see this clearly in systems like the mice galaxies, a pair of spirals tangled in long, beautiful tails of stars and gas. Those spectacular tidal tails are made of visible matter pulled out by gravitational forces. Yet, when we map the mass, we find the dark matter remains in a smooth, distributed cloud, largely unaffected by the drama. This collisionless nature is a core property, explaining why the dark matter components become so cleanly separated from the gas, as seen in the bullet cluster. These mergers are not just random crashes, they are choreographed by the dark matter halos themselves. The outcome of a collision, whether it creates a new elliptical galaxy or a grand spiral, is dictated by the mass, speed, and angle of the impacting dark matter halos. They provide the gravitational blueprint for the entire event. This makes collisions a critical test for alternative theories like WIMP. Modified gravity cannot easily explain why the gravitational lensing effect, the true map of mass, is found far away from the visible X-ray glowing gas in colliding clusters. Only a substance that is physically separable from normal matter can account for that observation. Our own cosmic future holds a front-row seat to such an event. In about 4 billion years, the Milky Way and Andromeda will begin their own slow merger. As the two galaxies entwine, their stars will be flung into new orbits, but their dark matter halos will effortlessly mix, creating a new, larger halo for the resulting elliptical galaxy, Andromeda. This process is a fundamental driver of galactic evolution. Major collisions trigger immense bursts of star formation, exhausting gas reserves and building up galactic bulges, effectively aging a galaxy rapidly. The presence and behavior of dark matter in these collisions directly influence galaxy formation timelines, determining when a galaxy matures and settles into its final form. By studying these cosmic impacts, we watch the invisible sculptor at work, shaping the universe not with brute force, but with the silent, relentless pull of its ghostly hand. That invisible hand began its work in the universe's very first moments. In the fleeting instant of cosmic inflation, a trillionth of a second after the Big Bang, the entire cosmos underwent a violent, exponential growth spurt. During this epoch, the quantum foam of spacetime itself rippled with tiny fluctuations. These were the primordial seeds, the faintest overdensities that would one day become everything. As the cosmologist George Smoot noted, dark matter is the invisible hand that shaped the universe, and this was the moment its fingers first began to curl. For millions of years, the universe remained too hot and energetic for these seeds to grow. This was the era of radiation domination, where light and other radiation ruled, constantly buffeting particles and preventing them from clumping. But dark matter, immune to this light's pressure, was already patiently waiting in the wings. The turning point arrived around 380,000 years after the Big Bang, at a pivotal moment called matter-radiation equality. This is when the density of matter, led by its dark component, finally surpassed the density of radiation. The universe's expansion cooled it enough for gravity to become the dominant force. Suddenly, the dark matter could act. Its relentless pull amplified those initial quantum ripples. pulling more and more invisible mass into the slightly denser regions. This set the stage for recombination when electrons and protons combined to form the first neutral atoms. With this, the cosmic fog cleared and the universe became transparent, releasing the light we now see as the cosmic microwave background. The Planck satellite's detailed map of this afterglow is a frozen snapshot of this very era. The subtle patterns in its temperature, the hot and cold spots in the CMB power spectrum, are a direct imprint of those dark matter seeds. The size and distribution of these spots tell us precisely how much dark matter was present and how its gravity had already begun sculpting the future. Then came the cosmic dark ages. For hundreds of millions of years, the universe was a vast black expanse of hydrogen and helium gas, silently condensing within the growing gravitational wells of the first dark matter halos. No stars existed yet. The only structures in the entire cosmos were these invisible scaffolds, these cradles of future galaxies. When a halo grew massive enough, its gravity finally triggered the collapse of the first dense gas clouds, igniting the very first stars and ending the dark ages in a blaze of cosmic dawn. This period of reionization, where the fierce ultraviolet light from these first stars ripped electrons from atoms, was itself orchestrated by the dark matter. The location and timing of these first lights were dictated entirely by where the dark matter halos had grown large enough to pull in the necessary gas. From there, galaxy assembly began in earnest. The peak of star formation occurred a few billion years after the Big Bang, a frenzied period of building where dark matter halos merged and accumulated gas at a ferocious rate. Our own Milky Way story is a product of this hierarchical growth. It began as a small, dense clump of dark matter in the early universe. Over billions of years, it cannibalized hundreds of smaller halos, each merger adding more dark mass and gas, steadily building the grand spiral we call home today. The invisible halo that envelops our galaxy is the accumulated legacy of this ancient construction project. So how did this single, unifying process of dark matter accumulation lead to the stunning diversity of galaxies we see today? The answer may lie in the smallest and most mysterious of them all, the dwarf galaxies that orbit our own. These tiny galactic islands are the purest expression of dark matter's power. Dwarf galaxies are the smallest and faintest known stellar systems, often containing only a few million stars, yet they hold the most profound secrets about our universe's invisible architecture. Astronomer Beth Willman perfectly captured their significance, stating that dwarfs are the purest tracers of dark matter. Their immense mass-to-light ratio reveals a staggering reality. In a typical dwarf, dark matter outweighs all the visible stars by factors of hundreds or even thousands. This makes them pristine laboratories, cosmic test tubes where the signal of dark matter is amplified and the noise of complex stellar physics is minimized. Their simple structures, often just a loose sphere of ancient stars, allow us to see the gravitational influence of dark matter with minimal interference. When we measure the motions of stars within nearby dwarfs like Fornax and Sculptor, we are not looking for orderly rotation. Instead, we track their velocity dispersion, the random, frantic speeds at which the stars buzz around within the galaxy's gravitational well. The data shows these stars are moving far too quickly for the meager gravitational pull of their visible companions. This high-velocity dispersion points to one inescapable conclusion. Each dwarf is crammed with an immense, dense core of dark matter, a concentrated knot of invisible mass that governs every stellar motion. This clear signal, however, has revealed a curious tension with our best simulations. This is known as the too big to fail problem. In sophisticated cold dark matter simulations of a Milky Way-like galaxy, The most massive subhalos, the ones deemed too big to fail at forming stars, are predicted to be incredibly dense. They should host bright, massive dwarf galaxies with intensely steep central concentrations of dark matter. Yet when we look at our own galactic neighborhood, the actual dwarf satellites we see, like Fornax and Sculptor, seem to have much lower densities. Their stars move more slowly than the simulations predict, as if the dark matter cores within them are less concentrated, more puffed out than expected. It is as if we predicted a bustling metropolis but found instead a quiet, sprawling town. Recent discoveries have deepened the mystery. Ultra-faint dwarf galaxies, found in deep surveys like the Dark Energy Survey, are so dim they were once lost in the vastness of space. These are barely galaxies at all, sometimes containing just a few hundred ancient stars. Yet their stellar motions indicate they are among the most dark matter-dominated objects in the entire universe. They may be the pristine fossils of the first dark matter halos, structures that formed so early that they never managed to accumulate much gas or form many stars, preserving a nearly pure sample of the universe's original dark matter. Studying these faintest of cosmic embers directly informs our understanding of galaxy formation itself. They show us the bare minimum of what a dark matter halo can produce, the absolute threshold for lighting up a corner of the universe. This journey from the largest cosmic web to the smallest dwarf galaxy brings us to the final, most extreme frontier. What happens where dark matter is most densely packed at the very heart of a galaxy, where its gravity might weave a trap from which not even light can escape? The galactic core is a gravitational maelstrom where dark matter's influence becomes intensely concentrated. At the very heart of a galaxy like our own, a supermassive black hole anchors a chaotic dance of stars, gas, and an invisible sea of dark matter. Physicist Priyamvada Natarajan has theorized that dark matter does not just surround these monsters, it may actively feed them. She suggests that dark matter dynamical friction can rob particles of their orbital energy, causing them to spiral inward and be consumed by the black hole. This process could provide a steady, invisible fuel source, helping to explain how these giants grew so large so quickly in the early universe. The density of dark matter here is not uniform. A compelling theory proposes the existence of dark matter spikes. As a black hole grows, its immense gravity can pull in and compress the surrounding dark matter halo, creating an area of exponentially increasing density right around the event horizon. Within this spike, the concentration of dark matter particles could become so extreme that they frequently collide and annihilate each other, potentially releasing a detectable flash of gamma rays. We can test these ideas by watching the stars that orbit perilously close to the abyss. Observations of stars like S2, whipping around our own Sagittarius, a star at blistering speeds, provide a precise measure of the central mass. Their trajectories act as a gravitational probe, revealing that while the pull is dominated by the black hole, it also places strict limits on how much additional dark matter can be crammed into the nucleus. Too much unseen mass would alter the orbits we see in ways that are simply not there. The implications of this central interplay are profound. In the early universe, the energy released from dark matter annihilation in these spikes could have acted as a powerful heat source, preventing gas from cooling and collapsing into the first stars, thereby indirectly shaping the timeline of cosmic dawn. This dynamic might also influence how often black holes merge. A dense spike of dark matter could slow two orbiting black holes through dynamical friction, hastening their inward spiral and ultimate collision, a process that could be detected by gravitational wave observatories. We see potential evidence in distant giants like the galaxy M87. The powerful jet erupting from its core is powered by the central black hole, but the stability and structure of that jet may be influenced by the shape and density of the surrounding dark matter halo, which provides the deep gravitational well that guides and confines the outflow. So if dark matter truly governs the hearts of galaxies, could its unique properties also hold the key to how the very first supermassive black holes were born? This question pulls our gaze from the brilliant core to the vast, sparse frontiers of the galaxy, where the ghost's grip takes on a different form. Far beyond the luminous spiral arms and bright central bulge, a galaxy's true extent is written in invisible ink. In these remote outskirts, stars become lonely sentinels, separated by vast gulfs of darkness. Yet this apparent emptiness is an illusion, for here, in the galactic halo, dark matter reigns supreme. Astronomer Amina Helmi notes that the motions of halo stars are like ancient records, preserving the history of our galaxy's assembly and mapping its unseen mass. This invisible ocean of dark matter dictates the paths of everything within its reach, from solitary, ancient stars to entire satellite galaxies and glittering globular clusters. To understand a galaxy's full weight and history, we must learn to read this ghostly text written in the fringes. Our own Milky Way provides the perfect observatory for this detective work. The European Space Agency's Gaia spacecraft is performing a monumental census, precisely measuring the positions and motions of over 1 billion stars. For those in the halo, their trajectories tell a gravitational story. These stars are not moving in orderly circles like those in the disk. Instead, they follow wild, plunging orbits, diving close to the galactic center before soaring back out into the darkness. These chaotic paths are dictated by the gravitational pull of the dark matter halo, allowing scientists to calculate its mass and distribution with unprecedented accuracy. It is like watching 1 million tiny buoys bob on the surface of a deep, dark sea, their movements revealing the powerful, unseen currents below. Some of the most eloquent tracers of this invisible mass are stellar streams. These are the ghostly ribbons of stars, the shredded remains of small dwarf galaxies or globular clusters that ventured too close to our Milky Way. Over billions of years, our galaxy's immense tidal forces, governed by its dark matter halo, have stretched these systems into long, elegant arcs that wrap around the galaxy. The Sagittarius Stream is a breathtaking example, a great circle of stars in the sky that is all that remains of a dwarf galaxy being consumed by our own. These streams are not random. They follow specific orbits dictated by the shape of the dark matter halo, acting as cosmic yarn strung around an invisible loom, tracing its contours with stellar precision. This mapping reveals that the dark matter halo is not a simple, featureless sphere. Detailed measurements show it possesses distinct properties that tell the story of our galaxy's violent birth. First is its triaxiality, meaning it is subtly squashed or stretched, more like a colossal potato than a perfect ball. This shape influences the paths of all orbiting objects. Second, the halo is not smooth. It contains a rich substructure of smaller, denser clumps, the dark matter counterparts of the stellar streams, which are the fossil remnants of past mergers. Finally, there is the splashback radius, a theoretical boundary that marks the edge of the halo. This is not a sharp cliff, but the point where matter that was falling into the galaxy reaches its farthest extent before settling back in, a cosmic high tide mark that defines the halo's ultimate frontier. We see this invisible architecture mirrored in our nearest large neighbor, the Andromeda galaxy. By tracking the motions of faint planetary nebulae in its halo and observing how its gravity lenses the light of distant quasars, astronomers have detected Andromeda's vast dark matter envelope. They found it is even more massive and extended than our own, a discovery that hints at a different, perhaps more violent, assembly history. The properties of these distant halos, these great spheres of invisible influence, are the ultimate archive of a galaxy's life. They record every merger, every accretion event, and every interaction across cosmic time. The silent, dark fringes of a galaxy hold the ledger for its entire cosmic budget, a tally of the invisible mass that has governed its growth from the very beginning. The cosmic budget reveals a startling imbalance. Of the entire universe's mass-energy content, the glittering stars, swirling gas, and every planet constitute a paltry 5%. Dark matter, the invisible architect, commands a staggering 27%. This precise accounting comes from our most robust model of the cosmos, LUX-ZEPLIN, a framework built upon 3 pillars of evidence. The Planck collaboration, after mapping the cosmic microwave background with exquisite detail, concluded that dark matter is a fundamental component of the universe's inventory. This inventory is not a guess. It is a convergence of data from the ancient light of the Big Bang, the measured expansion history from distant supernova, and the large-scale clustering of galaxies revealed by Baryonic acoustic oscillations. These independent lines of inquiry all point to the same cosmic recipe. To understand how we arrive at these numbers, picture the universe's critical density. This is the precise amount of matter and energy needed to make the cosmos geometrically flat, a key prediction of inflation. Without dark matter's substantial contribution, the universe would be starkly different, its geometry warped and its structure unable to form. The patterns in the cosmic microwave background are our most powerful tool. The Planck satellite's all-sky map is a photograph of the infant universe, and its subtle temperature fluctuations, the hot and cold spots, are a frozen record of those early density ripples. The size and distribution of these spots are exquisitely sensitive to the amount of dark matter present. Too little, and the patterns would not match the intricate cosmic web we see today. This is complemented by the evidence from Big Bang nucleosynthesis, which precisely calculates how much ordinary baryonic matter was forged in the universe's first few minutes. That calculation perfectly matches the 5% figure, leaving no room for dark matter to be made of ordinary stuff. So what does this budget sheet tell us about our ultimate fate? With dark matter and ordinary matter together making up only 32% of the cosmos, the overwhelming majority, a mysterious 68%, is something else entirely: dark energy. This invisible tension governs the expansion of space itself, and its interplay with dark matter's gravitational pull will ultimately decide the destiny of everything. 2 titans govern the cosmic arena, locked in a silent struggle that dictates the fate of everything. On one side, dark matter uses its gravitational pull to gather and build, sculpting galaxies and weaving the cosmic web. On the other, dark energy exerts a repulsive force, stretching the very fabric of space and driving the universe to expand at an ever-increasing rate. This is not a battle for destruction, but a delicate and eternal dance. As physicist Sean Carroll explains, dark matter builds the structures, dark energy determines their destiny. Their opposing influences create the grand narrative of our universe, a story of construction and dispersal happening on the largest scales imaginable. This cosmic tug-of-war directly shapes how galaxies evolve. In the early universe, dark matter had the upper hand. Its relentless gravity amplified the first tiny ripples, pulling gas into its invisible halos and sparking the birth of the first galaxies. Clusters grew and the cosmic web condensed, all under the architect's careful guidance. But as the universe expanded and grew more diffuse, dark energy's constant presence began to dominate. Its push started to overcome gravity's pull on the grandest scales, fundamentally altering the future of cosmic structure. We can observe the separate signatures of these two giants through brilliant cosmic beacons. Observations of Type Ia supernova, which act as standard candles for measuring vast distances, first revealed the shocking acceleration of the universe's expansion, the primary evidence for dark energy. Meanwhile, the imprint of baryon acoustic oscillations, faint ripples frozen in the distribution of galaxies, allows us to measure the history of how structure formed, tracing the competing pulls of dark matter's gravity and dark energy's repulsion. The implications of this duel are profound for the distant future. As dark energy's influence grows, the cosmic expansion will continue to accelerate. Galaxies that are not already bound together by dark matter's local gravity will be swept apart. The observable universe will become a far more lonely place, with island galaxies isolated in a vast and ever-darkening void, their mutual gravitational pulls eventually overcome by the stretching of space itself. Scientists probe this intricate relationship by running universe simulations on supercomputers, tweaking the properties of dark energy to see how the cosmic story changes. Some models suggest that if dark energy was stronger in the early universe, it could have suppressed the formation of the first galaxies, leaving the cosmos permanently dark and empty. Other simulations show how our specific cosmic timeline, with dark energy emerging to dominance only after billions of years of structure building, was necessary for us to exist. This invisible duo writes the rules of the game, defining the entire narrative from the first star to the last. To truly understand this cosmic choreography, we must learn to map the unseen dancer, to trace the dark matter that provides the stage upon which this epic plays out. These maps of the unseen are drawn with the most delicate of brushes. Astronomers act as cosmic cartographers, charting the invisible continents of dark matter that stretch across the sky. They accomplish this not by seeing the substance itself, but by meticulously measuring its subtle effects on the light from millions of distant galaxies. Large, ambitious surveys like the Dark Energy Survey and the European Space Agency's Euclid mission are at the forefront of this effort, using the phenomenon of weak gravitational lensing to create the first all-sky maps of the dark universe. As astronomer Sarah Bridle explains, lensing maps let us see the dark universe. They translate the ghostly pull of gravity into a visible landscape. The process begins with painstaking observations. Powerful telescopes capture images of immense patches of the sky, cataloging the shapes of countless faint background galaxies. In the absence of any distorting mass, these galaxies would be randomly oriented. But as their light travels toward us, it passes through the gravitational fields of foreground dark matter. This invisible mass ever so slightly bends the light, shearing the apparent shapes of the background galaxies in a coherent direction. Each individual distortion is minuscule, far too small to be seen by eye. It is only by analyzing the patterns across thousands, or even millions, of these galaxies that the signal emerges from the noise. This statistical whisper reveals the shape and density of the intervening dark matter. Sophisticated computer algorithms then take this sea of subtle distortions and use it to reconstruct a three-dimensional map of the invisible mass distribution, a tomography of the cosmic web. The path to a clear map is fraught with challenges. One major obstacle is shape noise, the natural, random variation in the intrinsic shapes of galaxies. Telling the difference between a galaxy that is genuinely stretched by dark matter and one that is naturally elliptical is a monumental task. Another hurdle involves measuring the distances to these galaxies. Surveys often rely on photometric redshifts, estimates based on the galaxy's color, which can have significant errors. A miscalculated distance can place a galaxy in the wrong slice of the cosmic map, blurring the final picture. Scientists mitigate these issues with immense data sets and complex statistical corrections, carefully cleaning the signal. The results are worth the effort. Projects like the Kilo Degree Survey, or KIDS, have produced stunningly detailed dark matter maps covering vast areas of the sky. These maps provide spectacular confirmation of the cosmic web, clearly revealing the dark matter filaments that connect clusters of galaxies like immense, invisible bridges. They also allow us to map the extended halos of individual galaxy clusters, weighing them with precision and confirming that their true mass lies in the dark component, not the glowing gas. What profound surprises might these first charts of the invisible world reveal about the fundamental architecture of reality? The answer lies in comparing these real-world maps to the predictions of our most advanced virtual universes. These virtual universes run on some of the most powerful supercomputers on Earth, translating the abstract mathematics of cosmology into a dynamic, visual story. Cosmologist Volker Springel calls these simulations our laboratories for the cosmos because they allow us to run experiments we could never perform in reality. Projects with names like Illustris, Millennium, and Eagle begin with the pristine conditions of the early universe, just after the Big Bang. They take the tiny fluctuations mapped by the Planck satellite in the cosmic microwave background and set them as the initial seed. Then they introduce billions of particles, each one representing a vast cloud of dark matter, and let the immutable force of gravity take over, fast-forwarding through 14 billion years of cosmic evolution in a matter of months. The primary engine for the dark matter itself is something called the N-body method. This is a computational technique that calculates the gravitational pull between every single one of those countless particles. It is an astronomically complex calculation, as each particle is constantly tugging on every other particle, shaping the destiny of the entire virtual cosmos. The result of this digital genesis is always the same, and it is breathtaking. From a nearly smooth beginning, a familiar structure emerges, the cosmic web, with its intricate filaments, dense clusters, and vast, empty voids, exactly as our telescopes have observed. These simulations successfully predicted the specific properties of dark matter halos, like their density profiles, long before our observational tools were sharp enough to confirm them. The Millennium Run, for instance, generated a virtual sky teeming with millions of these halos, providing astronomers with a detailed prediction of where they should look and what they should find in the real night sky. Yet these virtual worlds are not built on dark matter alone. To create realistic galaxies, the simulations must also account for the ordinary matter, the baryons. This is where the physics becomes incredibly complex. The models must include the hydrodynamics of collapsing gas clouds, the violent feedback from supernova explosions that can blow gas out of a galaxy, and the intense radiation from supermassive black holes that can heat surrounding material and shut down star formation. It is this delicate interplay between the dark matter scaffolding and the fiery, dynamic baryons that ultimately determines whether a galaxy becomes a spiral or an elliptical, and how many stars it will form. The stunning agreement between these simulated universes and our own is a powerful testament to the cold dark matter model. However, these same simulations also highlight the persistent small-scale problems, like the puzzling absence of the countless small satellite galaxies they predict around the Milky Way. This very tension is invaluable as it guides physicists to refine their models, perhaps by better understanding supernova feedback or by considering new properties for dark matter itself. These digital laboratories are not just recreating the past, they are actively guiding the future of our search, pointing our telescopes toward the most promising corners of the sky to find the invisible architect's final clues. A new generation of instruments is now searching for the ghost. Across the globe and in the depths of space, an unprecedented campaign is underway, deploying technologies of almost unimaginable sensitivity to finally identify the universe's invisible architect. Physicist Neil Weiner captures the collective anticipation, stating that experiments like LZ and Xeno-NNT are on the cusp of discovery, probing territories where dark matter must reveal itself. These are not mere upgrades, they are leaps into the unknown, designed to either capture a dark matter particle or systematically rule out the leading candidates, forcing us to rethink everything we know. In the silent darkness a mile underground, the hunt for WIMP has entered a decisive phase. The LUX-ZEPLIN, or LZ, experiment and its European counterpart, Xeno-NNT, represent the pinnacle of direct detection. They operate in a profound vacuum of background noise, shielded by rock and water, their hearts filled with tons of ultra-pure liquid xenon. They wait for the telltale flash and charge of a single, rare collision, a dark matter particle bouncing off a xenon nucleus. These detectors are so sensitive they could hear the whisper of a single radioactive decay from miles away. Their mission is to explore the most promising parameter space for WIMP, and with each passing month of silence, they tighten the constraints, closing windows on what dark matter is not. Above, in the clarity of space, a different strategy unfolds. The James Webb Space Telescope peers back to the cosmic dawn, studying the very first galaxies. Their formation, their brightness, and their structure are a direct test of our dark matter models. If small, bright galaxies formed too quickly or in unexpected patterns, it could challenge the cold dark matter paradigm, suggesting the particles were warmer or interacted in ways we have not considered. Meanwhile, the Nancy Grace Roman Space Telescope and the European Space Agency's Euclid mission are cosmic cartographers on a grand scale. They will map the shapes of billions of galaxies, using weak gravitational lensing to create the most detailed charts yet of the dark matter web across cosmic time. Euclid alone will observe over a third of the sky, tracing the invisible filaments that have guided cosmic evolution for billions of years. On Earth, other colossal projects are taking shape. The Simons Observatory and the future CMB-S4 project in Chile will stare at the cosmic microwave background with revolutionary precision. They will scour the afterglow of the Big Bang for the faint imprint of primordial dark matter or the subtle distortions caused by early dark energy. In radio astronomy, the Square Kilometre Array, or SCAR, will use vast fields of antennas to map the distribution of neutral hydrogen gas across the universe. Since this gas traces the underlying gravitational potential, its map is essentially a map of the dark matter, revealing the cosmic web in a whole new light. And back at the frontier of particle physics, upgrades to the Large Hadron Collider will push collision energies even higher, attempting to create dark matter in the laboratory by brute force. The goal of this global effort is twofold. The first is a definitive discovery, perhaps the identification of a WIMP or the detection of an axion converting into a photon in a strong magnetic field. The second, equally important outcome is exclusion. By ruling out vast swaths of theoretical territory, these experiments force a great narrowing, guiding theorists toward the true solution. They are closing the net, leaving fewer and fewer places for dark matter to hide. Will we solve this profound puzzle within our lifetime? The answer is uncertain, but the tools now in our hands are more powerful than ever before. This relentless pursuit inevitably brings us to the final, most profound questions that dark matter poses, the mysteries that remain even if we find the particle itself. Even with all we have mapped, the ghost refuses to give up its final secrets. We know dark matter is there, we can trace its gravitational shadow, but its fundamental nature remains one of the greatest puzzles in science. The physicist Catherine Fritz called it the ultimate mystery story, and we are still turning the pages searching for the final chapter. So what are the specific, stubborn questions that keep cosmologists awake at night? The most basic one is also the most profound. What is dark matter actually made of? We have candidates from WIMP to Axions, but we have not yet caught a single particle in our detectors. This leads directly to the next puzzle. Why does it not interact with light, a substance that is completely transparent, that ignores photons entirely, is bizarre from the perspective of particle physics? We must also ask how it behaves on the smallest quantum scales. Does it have its own hidden forces, a dark sector with its own rules that we cannot see? The ongoing debates are fierce. Is dark matter cold, moving sluggishly as our best models suggest, or could it be warm, with particles moving at a fraction of light speed, which would suppress the formation of small galaxies? Or is it self-interacting, with particles that can bounce off each other to smooth out the centers of galactic halos? Future data from telescopes like Euclid and the Roman Space Telescope will map the cosmic web in such detail that they should be able to distinguish between these possibilities, telling us if the ghost is solitary or social. There are also tantalizing, unconfirmed signals from the cosmos. For years, astronomers have observed a mysterious excess of gamma rays emanating from the center of our own Milky Way. This faint glow could be the signature of dark matter particles finally annihilating each other, converting their mass into pure energy, or it could be from a population of unseen pulsars. We simply do not know yet. Other puzzles abound. We still do not fully understand the nature of dark matter substructure, the countless tiny halos that should swarm around large galaxies. Are they truly there, just dark, or does our theory need revision? We question how the precise properties of a dark matter halo dictate the stunning diversity of galaxy shapes and sizes we see. And some theorists even ponder profound connections to cosmic inflation or multiverse theories, wondering if dark matter was forged in the very first moments of reality, a relic from a time before time. On the experimental front, the debate over results like those from the Dharma/Libra experiment continues to divide the scientific community. For over 2 decades, this experiment has reported an annual modulation in its signal, a rhythmic rise and fall that its team claims is the Earth moving through a galactic wind of dark matter. Yet no other experiment has been able to reproduce this finding, creating a standoff that highlights just how difficult this hunt truly is. The search for consistency across all experiments, from deep underground to the depths of space, is the driving force behind new theories and more sensitive detectors. These unanswered questions are not a sign of failure. They are the engine of discovery, pushing our understanding to the brink and inspiring a generation of scientists to look deeper into the dark. This relentless curiosity has moved beyond the lab, seeping into our culture and reshaping how we see our place in a universe dominated by the unseen. This invisible cosmic ghost has escaped the laboratory to become a modern cultural muse. Filmmakers, writers, and artists continually translate its profound mystery into works that captivate millions, building a bridge between abstract science and the human experience. The film Interstellar, for instance, wove the fabric of space-time and hidden dimensions into its narrative, making the warping influence of immense, unseen masses a central plot device. Philip Pullman's beloved trilogy, His Dark Materials, takes the concept even further, imagining a universe where this mysterious substance is a bridge to other worlds and the very source of human consciousness. Artist Raphael Lozano Hemmer, who creates installations that make the invisible tangible, perfectly captured this artistic drive, stating that his work aims to evoke a sense of wonder about phenomena we cannot perceive directly. He uses technology to create experiences where participants cast impossible shadows or trigger waves of light in empty space, making the audience feel the presence of an unseen force, much like dark matter itself. The vital link in this creative chain is science communication. Through breathtaking documentaries and immersive planetarium shows, complex ideas about galactic halos and gravitational lensing are translated into visual spectacles that everyone can understand. These narratives give the public a shared language to discuss the cosmos, transforming data into wonder. The metaphors artists use are particularly powerful. The very words dark and unseen resonate on a deeply human level. They tap into our universal experiences of the unknown, the hidden forces in our own lives, and the mysteries that lie just beyond our perception. This connection is explored in symphonic music composed with themes of cosmic voids, in educational video games where players build galaxies governed by dark matter's rules, and in packed public lectures that feel more like spiritual explorations than academic talks. One of the most compelling examples is the Dark Matter Museum project, an initiative where artists and scientists collaborate to create exhibits that are part data visualization and part sensory journey. Visitors do not just learn about dark matter, they encounter it through sound, light, and interactive sculpture, feeling the scale of its mystery in a personal way. How does this collective exploration of the invisible enrich our culture? It reminds us that wonder is a valid and vital response to the universe, fueling creativity and a shared sense of curiosity that transcends disciplines. This cultural engagement with the cosmic unknown naturally raises a more grounded question. What tangible benefits could come from finally grasping the nature of this ghost? The search for the invisible architect is quietly reshaping our world. While we may not yet control gravity or tap dark energy, the relentless pursuit of dark matter is already spawning a quiet technological revolution. Physicist Juan Coller observes that the hunt for these elusive particles forces us to push the boundaries of low background technology, creating instruments of almost impossible sensitivity. To hear the faint whisper of a dark matter particle, we must first learn to silence the entire universe, building shields against cosmic rays and crafting materials free from any natural radioactivity. This mastery over silence is now echoing into other fields. The same cryogenic detectors, cooled to a fraction of a degree above absolute zero to sense the faintest heat from a particle collision, are finding new purpose. They are being adapted to analyze the most delicate quantum states, a crucial step for developing stable quantum computers. The ultra-pure crystals grown for dark matter experiments are inspiring new types of sensors for medical imaging, potentially allowing doctors to see deeper into the human body with less invasive scans and lower doses of radiation. This is the hidden dividend of pure curiosity. It builds better tools for all of humanity. Beyond these immediate spin-offs lies a deeper, more profound payoff. Unlocking the nature of dark matter would be a monumental leap in our fundamental understanding of physics, revealing new particles or perhaps even new forces that operate entirely within a hidden dark sector. Such a discovery would not just rewrite our textbooks, it could illuminate new pathways for energy generation, perhaps through mechanisms we cannot yet conceive. It could revolutionize space travel by granting us a complete understanding of the gravitational landscape, allowing future navigators to chart courses using the subtle gravity wells of dark matter halos as cosmic landmarks. The very structure of the cosmic web could one day point toward untapped resources, asteroids and planetesimals gathered in the invisible gravitational pockets of dark matter filaments. The pursuit itself is a powerful engine for progress, inspiring a new generation of scientists and engineers to tackle seemingly impossible problems. It demands unprecedented international cooperation, uniting researchers across the globe in a shared, monumental task. These indirect benefits are the legacy of every great scientific quest. The long-term value of exploring the unknown is not always a specific gadget, but a sustained elevation of our collective capabilities and imagination. This journey into the dark is not a diversion from practical concerns. It is an investment in a future whose contours we can only begin to glimpse. And as we build these incredible machines to find the ghost, we are simultaneously preparing ourselves for the next great cosmic question, one that ties the architect's past to the universe's ultimate destiny. Our cosmic story is hurtling towards a profoundly dark and lonely finale. Cosmologist Lawrence Krauss captured this bleak destiny perfectly, stating, "The future universe will be dark and lonely, dominated by dark energy." For billions of years, dark matter has been the master architect, tirelessly building the great galactic cities. But its reign is finite. A silent war has been raging, a tug of war between the gravitational pull of dark matter, which builds, and the repulsive push of dark energy, which disperses. Right now, in our cosmic era, dark energy has already gained the upper hand on the largest scales, accelerating the expansion of the universe itself. For a time, dark matter's local influence will hold firm. Our own Milky Way, Andromeda, and the other galaxies of our local group are gravitationally bound, destined to merge into a single, giant elliptical galaxy. Within this future amalgam, dark matter will continue to orchestrate the motions of stars, its halo providing the stable scaffold for this new, larger city. But beyond our local island, the fate of the cosmos is one of increasing isolation. As the expansion accelerates, galaxies outside our immediate gravitational family will begin to redshift, their light stretching into invisibility. They will not fly away physically, but the space between us will grow so rapidly that their light can no longer reach us. The observable universe will shrink to include only our own merged galaxy, floating in an ever-darkening void. This is the future if dark energy remains constant, a force with unwavering strength. What happens to the grand architecture dark matter built? New galaxy formation will cease entirely. The dark matter filaments of the cosmic web will remain, but they will become stagnant. With space stretching so quickly, fresh gas can no longer flow along these invisible highways to gather and collapse into new stars. The era of star formation will end. Our simulations of this distant future show a universe growing cold and quiet. Over trillions of years, the last stars will burn out, leaving behind stellar remnants, cold dwarfs, and neutron stars. Even the supermassive black holes at the hearts of galaxies will, over almost unimaginable timescales, evaporate through a process known as Hawking radiation. And what of dark matter itself? Its story may not be eternal. Some theories suggest that over these immense durations, dark matter particles could be unstable. They might slowly decay into lighter particles, gradually releasing their mass energy and fading away. The legacy of this invisible architect, the sculptor of all we see, would then be a final, gentle dissipation into the cooling background of the cosmos. This is the heat death, the ultimate equilibrium where no energy can be harnessed and no new structures can form. So what legacy does dark matter leave in the cosmic story? It was the essential creator, the force that made a vibrant, star-filled universe possible, a temporary but brilliant flare of structure in an otherwise relentless slide toward emptiness. Its invisible hand wrote the only chapter of the universe's story that could ever be read, building the stages upon which stars, planets, and life itself could briefly emerge. The silent framework of the cosmos is now laid bare before you. We have traced the ghost from the frantic orbits of stars within spiral galaxies to the immense, invisible halos that cradle them. We have watched it weave the cosmic web, connecting glittering cities of galaxies with filaments of pure gravity, and seen its fundamental nature revealed in the violent collisions of galaxy clusters. This is not a theoretical abstraction. Dark matter is the fundamental sculptor of reality, the unseen architect that dictated the form of every galaxy and continues to guide its evolution. Its invisible hand touches everything from the majestic spin of the Andromeda galaxy to the faintest, most ancient dwarf orbiting our own. This understanding connects us to the universe in a profound new way. We are not just living on a planet orbiting a star. We are inhabitants of a vast, invisible structure, our very existence made possible by a cosmic framework we are only just beginning to map. This journey into the dark ignites both scientific curiosity and a deep human wonder, reminding us that the greatest mysteries are not always hidden in the light, but in the beautiful, shaping darkness. The next time you gaze up at the starry band of the Milky Way, remember that you are looking at the visible embroidery on a colossal, dark tapestry. Let that perspective fuel your own curiosity about the universe's deepest secrets. If this exploration reshaped how you see the cosmos, share this video to spread the wonder. Subscribe for more journeys into the heart of space's greatest mysteries. And in the comments below, tell us what aspect of this invisible universe captures your imagination the most. As Carl Sagan once reflected, somewhere, something incredible is waiting to be known.